Blockchains constantly emit signals: deposits, transfers, votes, mints, and contract changes. Event monitoring lets an AI agent listen in real time, identify what matters, and trigger useful actions across payments, DeFi, DAOs, and apps. So far, you've learned how agents think, use tools, connect to wallets, read blockchain data, and interact with contracts. Now we take the next step: agents that don't wait for prompts, but respond automatically when on-chain events happen. Think of a blockchain as a live signal network. Deposits, proposals, mints, and transfers are recorded continuously, but on their own, they are just data. Event monitoring helps an AI agent listen for the signals that matter. When one appears, the agent can trigger a payment, send an alert, call a contract, or make a decision. That is what moves an agent from passive reader to active automation layer. When a transaction runs, a smart contract can announce what happened by emitting an event, such as a transfer, mint, deposit, or proposal created. The blockchain records that event as a log inside the transaction receipt. Because logs are indexed, applications do not need to replay every transaction. They can filter by contract, event signature, block range, or indexed fields. For agents, these logs provide reliable, structured signals for understanding on-chain activity and deciding what should happen next. An event log is designed for fast searching. First, the event declaration, such as transfer address uint 256, is hashed into an event signature. That hash usually becomes topic 0, which tells indexers what kind of event this is. Any parameters marked indexed become additional topics, so applications can filter by sender, receiver, token ID, or proposal ID. Values that are not indexed go into the data field, where they are decoded later using the contract ABI. Blockchain logs arrive as hashes and hex values, so an agent should not infer meaning from them directly. The contract ABI acts as the translation key. It defines the event name, parameter types, and which values were indexed into topics. When your app calls getLogs, then decode event, the result becomes a normalized record: sender, recipient, token amount, token, or proposal ID. That structured event is what should enter the agent workflow. Efficient log monitoring starts by narrowing the question before you ask it. Begin with the contract address, so the node is not scanning every protocol. Then choose the event signature, like transfer or swap, to isolate the behavior you care about. If possible, add indexed parameters, such as a wallet, token ID, or proposal ID. Finally, keep block ranges reasonable. Overly broad filters create slow RPC calls, higher costs, and agents that react to noise instead of signal. Choosing how to detect events is a trade-off between freshness, operational burden, and cost. Polling is the simplest starting point: predictable, but request-heavy and not ideal for fast reactions. WebSockets reduce latency, but require reconnect logic, dropped subscription handling, and backpressure management. Managed webhooks move much of that work to a provider, which can speed production integration while adding vendor risk and recurring fees. Match the method to the event's criticality and your team's capacity. Polling works best as a disciplined loop. The monitor remembers the last processed block, then asks the chain for logs only within a bounded range, like 103 through 106. Each matching log is decoded, validated, and converted into a workflow input. After the agent handles it, the system records the event ID and advances the checkpoint. That checkpoint makes restarts safe, prevents duplicates, and keeps RPC calls predictable. WebSockets let an agent react as soon as a node sees a new block, log, or pending transaction. That speed is valuable, but the stream is not a source of truth by itself. Connections drop, providers may replay events, and reorganizations can invalidate what you just saw. A strong handler should reconnect, backfill missed block ranges, deduplicate events, and queue work for the agent. Before taking irreversible action, use polling checkpoints to confirm state. Managed webhooks let you outsource the event watching layer. For example, when a user sends USDC, the provider detects the transfer and calls your backend. Your backend should verify the signature, confirm the event, and use an idempotency key so retries do not create duplicate actions. From there, your agent can notify the user or trigger a workflow. The trade-off is vendor dependence. Supported chains, latency, pricing, and data quality all matter. A trigger should not mean do something whenever anything happens. It should define a clean chain. Detect the event, confirm it matters, choose the right response, then execute safely. A deposit might be checked against an invoice total before marking it paid and sending a receipt. A transfer might require compliance review before rewards or notifications. Good trigger design turns raw on-chain activity into reliable agent workflow, not random automation. Treat every event as untrusted until it passes several gates. Wait for enough confirmations before anything expensive or irreversible. Make reactions idempotent by recording a unique event key, chain ID, contract address, transaction hash, and log index. Then validate the details, sender, token, amount, and whether the emitted event actually means what your agent thinks it means. Finally, constrain the wallet with allow lists, spending limits, and human approval. Safety is not one check, it is layered friction. Event-driven agents become useful when a blockchain signal maps to a real action. A payment agent can mark an invoice paid after a stablecoin deposit. A DAO agent can track proposals, votes, and execution. NFT communities can react to mints or holder changes. DeFi monitors can watch liquidity, liquidations, or risk thresholds before humans miss them. You've now built the foundation for event-driven Web3 agents, reading logs, choosing monitoring architecture, designing smart triggers, and adding production safety. The key shift is from asking an agent questions to letting it observe, verify, and act. Next, we'll apply this to payments, escrow, markets, and multi-agent systems.